In this video, we take a look at acid and base theories, properties of acids and bases, the Arrhenius theory, Bronstead-Lowry theory, and the Lewis theory. So acids and bases play a central role in chemistry as they do in our daily life. Our body needs both acids and bases to perform properly. We consume acids such as vinegar, carbonated drinks, and citrus fruits, and sometimes consuming too many acids results in acid reflux, and we take a base, we take like a Tums or an antacid to then relieve that heartburn feeling. So some ways in which you can think of what makes something an acid is looking at some very distinctive properties of those acids. One is they taste tart or sour. You think of like biting into a lemon, and that soury taste you get when you bite into just a pure lemon or lime, one not like lemonade that's been sugared down, but one that is just pure, that citric acid, really tart tasting. Another is when they're put into solutions, they do release electrolytes. They do give positive and negative ions and allow an electrical current to be traveled throughout that solution. And they can cause some indicators to change colors. So if pH paper results in changing that pH paper to a red, an orange, or a yellow color. If it's litmus paper, that has the ability to change blue litmus paper red, and red would stay red. And that's how you know an acid, looking at pH paper. And they're very corrosive to metals. When we worry about acid rain and how it has an effect on structures such as like bridges that are made out of iron and how it causes the iron to rust and it corrodes down the metals, or putting like magnesium into hydrochloric acid, it chews it up really quickly. Bases too have very distinctive properties, one of which is they have a very bitter taste. If you ever had pure cocoa before or accidentally gotten like soap in your mouth, you don't want to taste too many bases because it's pretty hazardous for you to eat. But if you ever accidentally got soap in your mouth, that kind of bittery taste, or again cocoa, that is a very distinctive property of bases. As is the fact they're very slippery to touch. When you touch bases, they break down the proteins in your hands. Like if you accidentally got bleach on your hands, it feels very slippery. They too will form electrolytes when they dissolve into water. They also will change some indicators. If it's pH paper, then it shows purple, blue, or green. And if it's litmus paper, then it can change red litmus paper blue, and then again blue will stay blue. Another common one for bases is phenolphthalein. It turns a pinkish color when it's a basic solution, and for acidic and neutral, that is clear. A nice property of acids and bases is, again, they can neutralize each other. When acid and a base come together, they will neutralize to make a water and a salt. And that's why we take like Mylanta or Pepto-Bismol when you have an upset stomach, because it has magnesium hydroxide, which is then able to reduce down that stomach acid and take away that heartburn feeling. So there are three different theories about acids and bases of how they get classified. The first of which is from Arrhenius. Arrhenius first defined acids as compounds that had hydrogens which could ionize and give H plus ions in an aqueous solution, and bases were compounds that had a hydroxide and OH that would then also be reduced and ionized when put into water. So within those acids, we had monoprotic acids, ones that had one hydrogen to be released. We see that like hydrochloric acid. Diprotic acids, like sulfuric acid, because it has two hydrogens to be ionized in water. And triprotic acids, like phosphoric acid, because it has three hydrogens that can be ionized in water. However, not every single compound that has a hydrogen will give hydrogen ions when dissolved in water. Only those that are very polar covalent will be able to be pulled apart and ionized in water. So we see like with hydrocarbons, such as that is methane, CH4, that won't dissolve into water and it won't give up any hydrogen ions when put into water. Bases, again with hydroxides, most are very soluble when you have a hydroxide like sodium hydroxide, magnesium hydroxide, and they will again dissociate and give up hydrogen ions when they are placed into water. But these bases are extremely caustic. They do cause deep, painful, slow healing wounds if not immediately treated. Again, think about like bleach and what happens when you leave bleach on your hands too long. You want to make sure you get that washed off right away. However, Arrhenius' theory doesn't cover all acids and bases. It covers a good chunk, but there were still a lot of other compounds that would show these acid-base properties that didn't fit under this category. So there's actually two different chemists that were kind of working on this at the same time, Johannes Bronstead and Thomas Lowry, and independently they came upon this idea that acids and bases can be defined on hydrogen ion donors and acceptors. Acids would give up a hydrogen ion, and bases would be able to accept a hydrogen ion. So one particular substance that really doesn't fit in underneath Arrhenius' theory, but is an extremely basic compound, is ammonia, NH3. Look at NH3, you'd almost think that it's acidic because it has those 3 hydrogens. There's no hydroxide in ammonia, but ammonia is extremely basic, really high on the pH scale. So the reason why this happens is because ammonia has these 2 electrons which are available to accept a hydrogen ion, and since it can accept a hydrogen ion, make a coordinate covalent bond of that hydrogen ion, it is classified as a base. So every acid and base that was still classified as an acid or base under Arrhenius is still an acid and a base under Bronstead Lowry. It just now classifies other substances within that category that weren't there before. So now, since we have some weaker acids and bases that are now brought in, we have what are called conjugate acid-base pairs. These conjugate acid-base pairs are related through the gain and the loss of a hydrogen ion. The conjugate acid is the one which is giving up a hydrogen ion, and then conversely on the other side, the substance that has now lost that hydrogen ion and therefore would be the acceptor going back the other way in an equilibrium reaction is our conjugate base. So we'll take a look at a couple of different ways in which conjugate acid-base pairs are related to each other in a moment. And within every reaction, there's actually 2 separate conjugate acid-base pairs. So on one side, there'll be an acid with a base, and the other side, there'll be another base with an acid, and they'll actually match up. So you have 2 different pairs of acids and bases as that hydrogen gets passed back and forth between 2 different substances. So we have 2 substances on either side that are an acid and a base, and then they will make 2 separate acid-base pairs. So here we have hydrogen sulfide, the -1 charge, and a hydrogen fluoride, and then it's in equilibrium with that fluoride ion and dihydrogen sulfide. And we see from the left side to the right side, the HS negative, and then on the right side, H2S, again, a gain and a loss of a hydrogen. So we have an acid-base pair there. But then also between the hydrofluoric acid and the fluoride ion, we have an acid-base pair because we also have a hydrogen being lost from the left to the right and then being gained from right to left. And then from this, very similar to that H2S, we actually come across the fact that water has some very unique properties. Water can be both an acid and a base. It has the ability to gain a hydrogen and make a hydronium ion. It also has the ability to lose a hydrogen and make a hydroxide ion. So sometimes it's an acid and sometimes it's a base. We call that amphoteric, since it can be both an acid and a base, kind of like amphibian. So take a look at these 2 different instances. So here we have water as an acid. We have H2O with ammonia, and ammonia is going to accept a hydrogen, and therefore the water is going to donate a hydrogen. So the water and the hydroxide ion are an acid-base pair in this case, and the ammonia and the ammonium are an acid-base pair. Conversely, here we have vinegar or acetic acid being dissolved into water, and now the acetic acid giving up a hydrogen, making that acetate ion, is the acid-base pair, and then water, in this case, gaining a hydrogen, so water being a base this time, with the hydronium ion being its acid-base pair. Then lastly, we have Lewis acids and bases. And Lewis looks at the electrons here just like he did in his Lewis dot structures. And he calls a Lewis acid an acid that has the ability to accept a pair of electrons, and a base is a substance that has the ability to donate a pair of electrons to make a coordinate covalent bond. So those acids have, therefore, a shortage of electrons, and therefore the ability to take on 2 more electrons, again making a coordinate covalent bond, where a base is going to have 2 lone pairs of electrons that it has to be able to donate to make a bond. And a hydrogen atom has the ability to accept a pair of electrons because that H plus ion, therefore, could take on 2 more electrons, fill up its first shell there, and be perfectly stable. And again, a substance that has a free pair of electrons, a lone pair, or an unshared pair of electrons, therefore has the ability to accept that hydrogen ion and make a coordinate covalent bond with it. So we see that here with ammonia, again NH3, and that nitrogen had 5 valence electrons. It made 3 bonds with each hydrogen to get to 8, but still has 2 lone pair of electrons there. On the right there we see the boron trifluoride, where we have 3 fluorines bonded to the boron. Boron only had 3 valence electrons and made 3 bonds. Every fluorine now has 8, but that boron still has only 6. So it has the ability to accept 2 more electrons and make a covalent bond with that ammonia, that nitrogen that has those 2 electrons that aren't shared. And we see that then making this compound here, where again, nitrogen's donating those 2 electrons, the ammonia overall donating 2 electrons to that boron, with the boron trifluoride accepting those 2 electrons.